Good afternoon. This is CIVE 638, Sedimentation Engineering, and I'm Professor Victor Ponce from San Diego State University, Department of Civil Engineering, College of Engineering. And the subject today, or the number of the class today is 11-2. That means 11th week, second lecture, the second lecture of the week, second and last lecture of the week. The subject today is sediment transport, as a matter of fact, the chapter on sediment transport. And I do intend to cover, let me see. So we are going to cover today, expect to cover D12, 13, 14, and 15. We're going to get toward the latter part of the class to 15. So let me backtrack in here a little bit. First, let me say that I was very fortunate to attend Colorado State University. I chose to go there. I had already gotten a master's at Colorado State in the late 60s. And then I took a time in practice, and I practiced for 3 years. And then I decided to go back to school to get a PhD, because my intention, or my original intention, which proved to be correct, was to get into academia. And you need a PhD to be established in an academic institution, no matter where you are nowadays. So that's what I did. And I was lucky that I was there, and I had an opportunity to not only learn from some of the best professionals in the field of sedimentation engineering, because that was my specialty, by the way, sedimentation engineering, that I later got into hydraulics and hydrology and environmental. That's a different story. But my original root knowledge was in sedimentation, and continues to be in sedimentation engineering. So, and I say that because not only I had great teachers, but also great colleague students that I went with, and many of them went on to make their mark in the profession. And I have a story, or a legacy tale, to share with you. I think I already mentioned to you that over the course of the last 10 years, I realized that I had this knack for telling stories, and I decided to, and I was telling a story on the web every month. And it went on for 10 years. So that's 120 stories, out of which some of them are very good, in my opinion, and in the opinion of others. And I'm going to share a couple with you tonight. I call them very pompously legacy tale. I didn't know what to call it, so that's the word I invented. So the first thing we're going to do is we're going to watch this video of the legacy tale that I call a three-way split. It does show, in no uncertain terms, the complexity of the subject that we're dealing with, sedimentation engineering. In 1988, I wrote a paper entitled Ultimate Sediment Concentration, which we already covered this paper in the last session in detail. So you already know what it contains and how we wrote it. Interpreted a statement in Chapter 4 of the ASCE Manual number 54, Sediment, which interpreted a statement in Chapter 4 of the ASCE Manual number 54, Sedimentation Engineering, regarding sediment rating curves. The paper concluded that typical sediment rating curves show a trend toward a constant concentration of suspended bed material load at sufficiently high discharges. That was a conclusion of the paper, but that really was not my own conclusion. I actually derived that concept from the manual, directly from the, should we call it the Bible of sedimentation engineering at the time, 1975. And this was, we already were doing this in 1988. So 13 years after the manual had been published. What we did was to confirm with equations, with mathematics, with mechanics, what had been experimentally shown in the manual by Some researchers, I don't recall their names. One would have to go to the manual and get the original reference. But that graph that I just shown you, that I just have shown you, is in the manual, is part of the manual. It gets that much respect because the manual is a highly respected document.
The following year, right at the end of the spring semester, I visited Colorado State University in Fort Collins, my alma mater, where I met Professor Johannes Gessler accidentally in the hallway of the College of Engineering.
Johannes Gessler, when I was there in the middle 70s, he was a junior professor. Exactly what he was teaching, I don't recall, and it was not my business at the time. But he was there already in the middle 70s when I was a student at Colorado State. Subsequently, the professor that used to teach sedimentation engineering, which was my professor, Daryl Simons, retired. Everybody's going to retire. He retired, and Johannes took over the class, the teaching of sedimentation engineering. I'm not sure if he was the only one, but he was definitely the professor at the time I was there in 1989 when I visited Colorado State.
Guest in the hallway of the College of Engineering. Gessler accidentally in the hallway of the College of Engineering. Gessler said, "Ponce, can I buy you a cup of coffee?" I answered in the affirmative, and we had coffee at the Student Center cafeteria, the site of many memorable experiences during my years at CSU in the late 60s and early 70s. During the conversation, Gessler confided to me, "I want you to know that I was so impressed by that paper that you presented at Colorado Springs last year that I decided to do something different this year in my graduate class in river mechanics. I told the students that the final would consist of an analysis of your paper. There were 12 students in the class, and there was a three-way split. 1/3 thought the paper was great and that it had clearly thrown additional light on the subject. Another third said that the paper was faulty and that the concepts expressed were outright wrong. The last third said that they couldn't figure it out for sure."
So that's the story. And as you guys realize, it is a tough subject. It is a tough subject for all of us every single day. It was a tough subject for Einstein, and he is going to tell us that it is right now. We're going to read his paper later. So it was a tough subject when the elder Einstein told his son, to get into this field because nobody knows anything about it. That was 1928. So that is one of the toughest subjects, and because it is not only mechanistic, meaning mechanics, it also has probability in there. So it's a combination. It's a good combination of both the two rules of nature. I guess you could say the physics, the mechanics, the determinism, and then the probability, which is not subject to deterministic laws. And both of them have are included, or I guess you could say should be considered in any analysis. The fact that we sometimes forego determinism or sometimes forego stochastic conditions is just a way of solving it. But every project or every item that we consider has both components. So that's the story. And as you can see, the students were split. Some thought the paper was great. It had solved the problem, as I think it has. Others said, no, it's no good. And others said, we don't know. We honestly cannot emit an opinion. So what is really the truth of the matter? I will explain it later. Okay, let me just finish with this and we'll come back later to explain what is the actual truth of the matter as I see it. Okay, so that's one story, a three-way split. And we have another story here, which is called the sediment rating curve, which is related to what we had just seen. So I'm going to show that video too.
In the summer of 1989, I went to Santa Cruz de la Sierra in Santa Cruz, Bolivia, on a consulting assignment in relation to the flood control scheme for the Piraí River Basin. My assignment was to do the sediment routing, that is, to establish the rates of sand deposition on several critical reaches of the Piraí River. At our first technical meeting, I proposed to use the Kobe method for sediment transport in the sand bed channels and the Meyer-Petermuller method for coarse sand and gravel transport. My proposal met with the opposition of one of the supervisors who argued that the Colby's method applicability to Bolivian rivers had not been demonstrated. I countered that I saw no other method better suited for sandbed rivers and that quartz sand was quartz sand everywhere. Since there is no sediment transport method specifically developed for Bolivian rivers, we use the Colby method, pending field verification. The field data was collected in the winter of 1990. We plotted the sediment rating curve, a plot of sediment discharge versus water discharge, and proceeded to compare measured and calculated sediment transport. To everyone's amazement, the agreement was excellent, showing measured sediment discharge closely matching calculated sediment discharge throughout a wide range of water discharges. Thus, I proved my point. The quartz sand was the same, regardless of location, and the Colby method was applicable to the Piraí. Closer examination of the data revealed, however,
let's take a look at this. Is this good agreement? I think it is. Anybody in the right mind would say, yeah, it's pretty cool. If you did a correlation, found a correlation coefficient, my guess it would be on the order of 90%. And anybody would agree that 90% is a good correlation. But this is a logarithmic curve on both sides. On the ordinates, the sediment discharge is logarithmic. And on the abscissas, also, the water discharge is also logarithmic. And I can't pull it up here, but you can see that there's at least 3 orders of magnitude variability. 1, 2 in the data that we measured, which we cannot control completely. At least in the water, we can't control it, but there's 2 orders of magnitude here. So as you can see how we plotted the rating curves that we had calculated based on the formulas and then the data points. But if you look at these data points, you'll see that, for instance, if we're looking at Colby here, okay, we're missing it here and here. The number is 25 and the actual Colby is 14. And the actual Colby in here is 82 and the actual number, the data measured is 100, or that's right, 104, 100 and yeah. And here it's even, well, here's right there. And here it's not, like here it goes from 40 to 70. So the errors, 20, 30, 40, 50, even 100% errors, but they are acceptable, accepted errors in terms of the accuracy that overall accuracy that we're talking about here.
That individual measured data points could be in error by as much as 100%, a fact well known by experienced sedimentation engineers. It is almost impossible to get a perfect match when dealing with sediment transport rates, which typically vary several orders of magnitude from low flow to high flow.
Okay, the next subject we're going to cover today is the D14, effect of form friction on the sediment rating curve. This paper was written by myself with Smith, I believe his name is David Smith, and Rosa Aguilar. we have it in raster and vector form. In this case, I'm going to do the vector form just for the heck of it. So I'm going to show the effect of form friction of the sediment rating curve. First, I should tell you who my co-authors are. I believe, yeah, Dave Smith is project engineer with West Consultants in Rancho Bernardo here in San Diego. Dave was a student, I believe, in the early 2000s. It could have been the year 2000. He got a master's degree with us. So he's been practicing out there for 22 years, presumably, as far as I know, with West Consultants. He is number 2 out there at West Consultants. I honestly don't know how many employees or engineers they have in San Diego. They've got 6 or 7 offices throughout the Western United States. They call themselves West Consultants. They have them in various places. I believe in Seattle is their head office. They're a good company if you want to work with in water, sedimentation and stuff, hydraulics. They're a good company to work with. I believe, if I remember correctly, what the manager told me many years ago, they used to have 60 or 70 employees. I'm not sure if the employees is everybody or just the engineers, but so be it. They're, I would say, a small to mid-size, well-recognized company in the area. And all they do is hydraulics. That's all they do. So they're specialists. That's Dave Smith. And Rosa Aguilar is a grad student, was a grad student. She was with us from the year 2012 to 14. She signed up with us. And the way it worked out is that I wanted her to learn web stuff, because people come to me without knowing any web. So I said, you gotta learn web stuff, HTML and so forth, PHP. She also learned PHP, by the way, over the 2 years she was with us. So I charged her with taking that paper, this paper that had been written by David and I 20 years earlier, not 20 years, maybe 15 years earlier, and put it on the web. So that merited that she was also the co-author. So there was a third author, myself, Dave Smith, and Rosa Aguilar. This work was mostly in content. It was done in original content, let's put it that way, was done by Dave Smith, because he had a friend. His friend, actually, I should take that back. It was not his friend. It was a gentleman that owned West Consultants. He was basically his boss. And his boss had gotten a PhD at Colorado State. And the work he did with one of my very esteemed professor, Professor Everett Richardson, was he had gathered data from a whole lot of sources around the United States. I believe he covered 50 sediment transport equations, 50 on that order. So he did some of the most comprehensive comparisons of sediment transport. Unfortunately, I didn't have access to his dissertation, but I know that for a fact. So since Dave was working with this gentleman, whose name at this point I don't remember, Dave had ready access to the data. So he was able to pull from that complete set of data, the data that we needed to write this paper. Because I told Dave what we needed to do. And they, of course, are very adept at handling data. So Dave did an excellent job in putting this thing together. I provided the original guidance or the conceptual guidance for this. So let's take a look at what we did in here. I think this is a very important paper. One of the very few papers on the subject. Also, it is a paper that has not been published in a journal, only in a proceedings. I believe we published this in proceedings. As you guys know probably well, and I don't know if you do, but there's 3 ways to publish. Nowadays, you publish in a journal, which is considered to be a referee journal. And when you write in a referee journal, the paper is reviewed and refereed by at least three people. And they have a say as to the paper is good or not so good or bad. If it's bad, they decline to publish it and so on and so forth. If 2 reviewers say yes, it gets published. Okay, it sees the light of day. So that's the story with these papers, with the journal papers. Now, the second tier is the proceedings paper. In the proceedings paper, generally, there's no three-member or three-person peer review. It's usually one, and it's very cursory review. So it's easy to publish in the proceedings. A lot of people publish in the proceedings. A case in point, we are about to start next week, as a matter of fact, the 30th issue or the 30th occurrence of the Latin American Hydraulics Conference, which is going to take place in Foz do Iguaçu, Brazil. And the reason why I bring that up is because they had a call for papers. Like in every conference, you have a call for papers, where 720 papers showed up, or something on that order, more than 700. And customarily, they call the papers, they select the best paper, maybe a third of them, usually a third of them, 200, 300 papers. They tell the rest of the people they're not going to publish it, and they run the conference with 300 papers. But in this case, for whatever reason, and they're only the ones that can decide these things, they decided to accept most of the papers. I don't know exactly how many, but I know that 720 papers were slotted for publication and presentation. So that was, it was good that you have a lot of quantity, but it was bad that with the quantity, you don't get the quality. And subsequently, they restricted their presentation to, I believe it was 8 minutes, 5 minutes for the virtuals, whatever it was too short. So Professor Ponce decided not to attend because I wasn't going to haul myself all the way to Brazil for a 5-minute presentation. And I didn't do it. But the paper is still there. I mean, it could be read by many people and so on and so forth. So that's the story. And the third type of presentation, mode of presentation, is the one that you publish directly on the web. Now, we didn't used to have that 25 years ago. You know, the web started in 1994. So it's been exactly almost 30 years now. In the year 2024, it's going to be 30 years since the web was operational. And prior to that, you couldn't do it. You had to either publish a report that nobody would read. Anybody can publish a report locally, but nobody would read. And those that wanted to read it would have to look for it, and it was difficult, not impossible, because we used to have, and they still have, I believe, with the system that's called interlibrary loan, where you can get a publication from any place in the world as long as you solicit it and they give it to you. So those are the three ways. But with the web, many people started to publish directly on the web. And I decided to do that from the beginning. Well, from the beginning of my involvement. My involvement was in 1999. 5 years after the web had been started, I got smart and I said, this is the way to go. So I started publishing on the web. By 2003, I had let's say two personal, I guess you'd say magazines or whatever, but where I published all the stuff. And I got about, I don't know, 100 pages, 100 reports and technical reports that was never saw the light of day in a journal or a proceedings. And one of them is this one. Actually, this one saw it at a proceedings. But that's a long story that I'm going to tell. I'm trying to tell you here because you must know what are the instruments in order to get published, because some of you may decide to do this later on. Okay, so you're young and you're getting started, and you may want to pursue this path. It's a very good path to pursue if you're getting into the pursuit of knowledge, as I had for almost 50 years now. So let's take a look at this paper. Effect of form friction on the sediment rating curve. Now, I bring this up because subsequently we're going to get into Einstein's paper today. And Einstein was one of the first, he's actually credited for being perhaps the first to separate mechanically and computationally the form friction from the grain friction. Grain and form friction. Grain is the friction that is produced by the grains themselves. So it's that friction is affected by the grain diameter, which you know could be either D50 or D84. Remember, we talked about that already. And the form friction is affected by the size of the forms, of the bed forms, the ripples and the dunes, and in certain cases, even the anti-dunes. But that's a form friction which is an order of magnitude, at least an order of magnitude greater than the grain diameter. So how does the form friction affect the sediment rating? That's the issue here. We got that smart because we had already looked and written that other paper that I just finished talking about. And then after that, I realized, because I read and reread Einstein, and Einstein does give us the clue in his paper. He said, if the water is busy handling the forms, is not going to produce that much sediment transport. I think he said that, not in those words, but we interpreted that to be the case. In other words, we felt that if you look at this, you're going to have in here a drop of this on the sediment transport, but it's going to go up, and eventually it's going to become a parallel, or rather a 45-degree angle, which means the concentration is going to be a constant. So here the concentration is not a constant, and it is increasing very sharply. And over here, the concentration gets to be a constant. Okay, if we plotted that against with the individual data points in here, that you can see there's about 100 data points in there. The 100 data points that David Smith was always able to get from that dissertation that I'm telling you, they considered 50 sediment transport formulas. And if you plotted the friction, it would be like an X. Can you see the X in there? That is an X. Admittedly, there's a lot of scatter, but that's within the issue, that's within the normal scatter of sediment transportation equations. What are we having here? And this is not a good thing to present because it is reduced, but over here we have sediment transport, water transport, and here Manning's in. So it's a double scale. So let's take a look. We say 6 measured sediment rating curves are examined through a wide range of discharges. At high discharges, the sediment rating curve tends to asymptotically approach a maximum sediment concentration. At low discharges, a documented drop in sediment concentration is attributed to the effect of form friction. A comprehensive field and laboratory data set is used to show that at low discharges, total friction, grain and form, and sediment concentration are inversely related, with form friction accounting for a significant portion of total friction. At high discharges, form friction is reduced to a minimum, with total friction and sediment concentration approaching a constant value. Thus, at low discharges, form friction effectively reduces sediment concentration to values below that which could be attained at high discharges. And I believe, okay, I'm gonna get there, because I added a line in here after the fact when we found out that Einstein had also said this. So the computation of sediment transport is fraught with difficulties, including the role of form friction in grain and form. Armoring, also an important thing. Armoring refers to the fact that if you have large diversity of grain sizes, eventually the small grain sizes are going to leave because of the energy of the flow, but the big ones, the boulders, are going to stay, and they are eventually going to armor the surface, and they will stop. They will effectively stop the transport. That's called armoring. Flow unsteadiness, yes, we have flow unsteadiness all the time. Despite these difficulties, it is usually possible in practice to develop a sediment rating curve. We count on sediment rating curves and being able to develop them. However, these should be steady, by the way, because the sediment rating is really a very complex issue. You can have hysteresis in there, not just one curve or one loop of hysteresis. You could have an 8 in there, a hysteresis in the shape of a number 8 and so forth. But we usually don't look at that because it's too complex for us to analyze. And we usually consider the sediment rating curve as being one solid, unique curve. Okay, sediment rating curve plot of bed material discharge in tons per day versus water discharge CFS on a log-log scale. That's usually the case. The rating curve has a tendency to asymptotically approach a maximum sediment concentration. And we quote the American Society of Civil Engineers. That, we already repeated that many times. Ponce examined this feature of the sediment rating and referred to the maximum value as the ultimate sediment concentration. We already examined that paper. The nature of the sediment rating, where the concentration A increases with discharge at low discharges, and B is asymptotic to a maximum value at sufficiently high discharges, suggests that there's a mechanism acting to reduce the sediment concentration at low discharges. It is surmised here that this mechanism is form friction. So we're saying it is form friction. Objective is to study of this study is to show, using high quality field data sets, that form friction is primarily responsible for the documented curvature and shape of the sediment rating at low discharges. So we didn't do any laboratory analysis or laboratory studies. We leave that for people that can do that. They have the large flumes like at Colorado State University, like the flumes that Professor Simons used in his research in the late 50s. So it will be confirmed that the sediment rating curve has a tendency to asymptotically approach a maximum sediment concentration. The net effect of form friction is to produce a drawdown of the sediment concentration below the ultimate value. So a drawdown over here. So this is a drawdown over here. It draws down the curve. If it were not for that, this would have to be straight. In other words, if this would be a straight line, horizontal line, then this would come back in here and raise itself up. That is our theory. Now we go back into the big guy, Einstein. Einstein, 1950, that is the classical paper by Einstein. Hans Einstein, the son of Albert. Apparently the first to separate total alluvial channel friction into its components, grain friction and form friction. He argued that the part of the energy spent on form friction does not contribute to the bedload motion. Let me repeat that because that's important, because it kind of reiterates everything we just said so far. He argued that the part of the energy spent on form friction does not contribute to the bedload motion. Therefore, it could be neglected in the calculation of the sediment load. It could be neglected in the calculation of the sediment load. So he didn't use that part of that energy, that part of the fraction of the energy in the calculation of his bedload function. This fits admirably with our conclusion that the effect of form friction is to reduce sediment load below that which could be attained solely by or with grain friction. So we first take a look at the field data set. In this study, we use the data assembled by Williams, Wright Williams. I still don't remember his first name, but he was the guy that did the PhD in the middle 90s with my professor, Everett Richardson. And he produced a huge, very thick volume. Williams produced a digital database comprising data used by Ackers and White in their own original methodology, 1973. Brownlee as well. Brownlee has also his own methodology. Engelund and Hansen and Yang. These are the four big guys. And all that data was collected by Williams in the middle 90s. The Brownlee data set included 7,000 sets of field and laboratory data. I think I already told you, Brownlee was a professor over at Caltech for many years. Williams filtered the data to include only points with the following features: gradation coefficient less than 5, sand median grain sizes in the 0.06 to 2 millimeter range, aspect ratio greater than 4. Aspect ratio is the width to depth ratio of the channel. He wanted to be not hydraulically wide. Hydraulically wide would be 10, but he didn't want to have how can I say, very narrow channels. If a channel has an aspect ratio of 2, it's a narrow channel. And it usually doesn't happen, by the way. Nature doesn't like narrow channels, for sure. If you go out there and look for a narrow channel in nature that nature has put together, it almost does not exist. Okay, I've seen 1 or 2 in my entire practice. I saw one in Colorado. I remember there was only 2 or 2.5 width to depth, but that was because of some other issues. When nature has its own way, the aspect ratio is usually 8, 10, 15, 20, even greater than that. Width to depth, which we call the aspect ratio. Aspect refers to the way it looks, by the way. the way it looks in the English language, aspect is the aspect. You can look it up. Look up the meaning of aspect if you're a bit confused as to the actual meaning. Because I was, when I first started doing this, I say aspect, why aspect? But that's the correct way of saying it. Hydraulic depth to mean grain diameter ratio greater than 100, and measured sediment concentration greater than 10 ppm. Yeah, 10 ppm is already too small. So he kind of filtered the data to have good data that he could analyze and rely upon for his own conclusions of the study. The following 6 sets of Brownlee's data were used for the present analysis. So Dave Smith picked up 6 sets of Brownlee data. There's a lot of Brownlee data, but he picked 63 points from the Atchafalaya. That was Toffeletti, 40 points from the Niobrara River, which was the one that Colby and Hembry had put together. Our next job next week is to look at the Colby and Hembry report, by the way, which is going to lead us to the main, should we say, to the main method of the whole course, which is the modified Einstein of Colby and Hembry. 38 data points from the Middle Loop River. Middle Loop River, I believe, is in Nebraska. 51 data points from the Rio Grande. Rio Grande is in Texas. 156 data points from the Mississippi. Toffeletti, that's a lower Mississippi, I believe. Because the lower Mississippi has upper Mississippi, lower Mississippi, and so forth. 29 data points from the Red River. The Red River is, I believe, I'm not 100% sure. It's in Arkansas somewhere. It's a tributary of the Mississippi. Within each data set, each data consisted of the following: water discharge channel width, hydraulic depth, bottom slope, mean grain diameter, gradation coefficients, sediment specific gravity, measured sediment concentration, and water temperature. And the Niobrara River data set also included bed form type. Methodology and results. The measure sediment rating curves, including a graphical best fit, are shown in figures 1A to 1F. In addition, for each data unit, the water discharge channel width, hydraulic depth, and bottom slope were used to calculate Manning's N, right? He had all the data, so he could calculate the Manning's N. For simplicity, channel shape was assumed to be rectangular. And that's why he wanted this aspect to be more than 4. Otherwise, he was going to make a mistake. For each data set, the calculated values of Manning's N were plotted on a secondary y-axis so that the trend in sediment rating could be readily compared with the trend in Manning's N. In all cases, it is clearly shown that Manning's N decreases as the water and sediment discharge increase. And we did this plot, I believe. Yes, we did this plot. Actually, I'm not sure if it was done by Rosa or by Dave. It doesn't matter. It was done by us. Okay, so now we're going to take a look at these graphs. A good look. There it is. Is there a correlation in here on the Mannings? I believe there is. I believe there is. It's a low correlation, but there is a correlation in there. So this is an X really between the black or the blue points, which is the sediment transport rating, and the magenta points, which are the friction. So the friction should be considered on the right side, and the sediment transport on the left side. So that is the first one. This is the Atchafalaya River. Uh-oh. Lost it. I know what it is, but I'm not going to complain at this point. Okay, this one is the Niobrara River. This is a better correlation. This is a better correlation. So that's the Niobrara River. Again, as you see, I forgot to do something that I should have done, which is put the HTML in there. Okay, so number 3, that's also a good correlation. Okay, let me see if I can go in here. I probably won't be able. You see, I won't be able to. I messed up. I'm sorry. I messed up. I should have prepared it, but I didn't get around to it or didn't notice it before. So we're back in here now. I'm not going to show any more. One more I'm going to show. This one, well, I mean, you can see them from here. This one's nice too. This one's a better one. That's the one we showed on top because it was a good one. Likewise, this one's a good one too. Let's take a look at this one right there. It's good. That's good. High correlation. So we are correct in what we said. We are totally correct in what we said. Let me just finish in here. Let's go back to the paper so that we can close it. Okay. Okay. Conclusions. Using high quality field data sets, it has been shown that form friction is largely responsible for the documented curvature and shape of typical sediment rating curves. Specifically, we have confirmed that at high discharges, sediment rating curves have a tendency to asymptotically approach a maximum sediment concentration. I personally have not seen any sediment rating curve that does not have a curvature, provided, of course, that they cover a wide range of sediment and water. If it's a narrow range, they don't have to show a curve because they didn't get that far. Conversely, at low discharges, form friction acts to reduce the sediment concentration below that which could be attained if form friction were to be negligible. Sediment rating curves were plotted for 6 high-quality data sets. These are supposed to be very high-quality data sets. They were used for the development of the original methods, the Ackers and White, Engelund-Hansen, Brownlee, and so forth. It is concluded that at low discharges, form friction has a significant role in reducing sediment transport, effectively decreasing the sediment concentration substantially below the ultimate value. At high discharges, form friction is reduced, total friction tends to be to a constant value, and sediment concentration approaches asymptotically the ultimate value. These findings clarify current understanding of sediment rating curves in particular and sediment transport in general. So now we are going to answer the question or try to provide a little more light into the question of that was posed by the students, or actually the question to the students by Professor Gessler. He asked them, what do you think about Ponce's paper? All of them read it. As a matter of fact, it was an exam. It was a final exam. This is how important the subject was in the mind, or in the mind of Professor Gessler. He said, this is good. I'm going to test the ability of my students to discern if Ponce was right or how right he was. And as you know already, because I already told you the story, a third of them said it was great, a third of them said it was really bad, and the third said, I don't know. They were honest, I guess. Honest in their, I guess you could say, inability to come up with clarity. So now I'm going to try to throw some clarity in there, because we wrote the paper, okay? But the objective of our paper was to show that this thing was happening. And I believe we did say, we could go back in there if we wanted to, we did say that there were some caveats, some qualifications. And I think the main qualification was that it had to be only bed material transport. That is correct. That you could not consider in their wash load. Because if you considered wash load, if wash load was part of the problem, it threw a monkey wrench into the problem. And Einstein has also repeated this extensively. The wash load cannot be calculated. Everybody that has done work in sedimentation, with only one exception, and I'll get to that later on, has avoided dealing with wash load. Because since wash load is hydrologic, it is not hydraulic. And if it's not hydraulic, then we have a hard time figuring out exactly what is going to be the quantity. We always say the quantity of wash load depends on the source, and the source could be anything. It's a stochastic issue, it's not deterministic, right? So we avoid even talking about wash load. The only person that made that exception was Colby and Hembry in their method that we're going to extensively take a look at next week. So that's the issue with the wash load. But in our paper, we said we should exclude wash load. And I was not privy to the answers of the students. All that Gessler told me was that there was a third that said very good, third that said no good, and a third that said we don't know, we can't figure it out. But in our paper, it does clearly say that exclude wash load. If you exclude wash load, everything we said was okay. If you include wash load, or rather if you make wash load part of the problem, we may or may not be 100% correct. That was the understanding. So anybody that said that, they would have qualified it in the same way we did, because wash load is a thing that we really can't control too much. What happens is that when you have a lot of wash load, okay, the wash load interferes with the bed load, and therefore it kind of, messes things up. It would be ideal to have a whole lot of transport and no wash load, but that's not true. Every time you have a whole lot of transport, there's always a certain amount of wash load. So with that qualification, our contention is that our analysis is correct as long as you do not consider wash load in there, which is a very big limitation, by the way. It's not easy. Why? Because if you're looking at high discharges, you're always going to have some wash load. So you can't say, I'm going to treat high discharges, but I'm not going to deal with wash load. That's unrealistic. So having said that, I think that is the explanation for the fact or for the merit of this methodology. I should say that in Manual 54, there is no such explanation. In Manual 54, the writers of that chapter, it was chapter 7, I believe, of Manual 54. We can go back to it. I'm telling you, Manual 54 in here, I have consulted it extensively over the last 40 years. The people that did this, that put this graph in the manual, that's all they said. This is the tendency. See you later, guys. We're not going to talk about it. They didn't analyze the situation as much as we had, as much as we did, without actually answering completely the question. So it still remains an issue whether this methodology is 100% correct. And I think I'm going to reiterate, it's 100% correct as long as you don't consider the effect of wash load, which is a big if anyway, because wash load is there. So with that, I have completed the discussion on the issue of the paper that Dave Smith and Rosa Aguilar put together. Okay. So then our next subject is D15. This is the big one. It's the actual Einstein paper. So that we're going to do today. We have about 25 minutes. And I am not going to get into the details of the math for two reasons. First, it will take us too long. We'll never get there. We'll waste our time. And second, the math of the mechanics, by the way. And second, it is not that important. I believe it's more important that we understand why and what did Einstein do, because it is an important contribution, and besides he's Einstein, right? We have to recognize he's a big name. So that's what I'm going to do. I'm going to start reviewing with you. No, that's not it. That's not it. Here or here. There it is, PDF. The bed load function for sediment transportation in open channel flows. Very well-known paper. Everybody claims to have read it. I venture to say that very few people actually have read it completely. I'm going to confess that I haven't either. I may have read maybe 90, 95%, but not all of it. There's a few things in there that I guess I'm not smart enough to understand. That doesn't stop me from talking about the 90% that I understand, by the way, because after all, I'm never going to be in Einstein's shoes. What we're trying to do in here is to understand the concepts so that we can apply it to other methods. And basically, I think I already told you this, and I'm going to reiterate it. Hardly anybody uses the Einstein method. Let me repeat, it's important. The Einstein method that we're going to talk about today, that we'll briefly talk about it, hardly anybody uses it. What people use is the modified Einstein and the Colby. But you guys understand, you could not have modified Einstein without having had prior to that the Einstein. So we're going to go to the root of it. And then in the midst of it, we're going to drop it and go back next week, or rather move on next week to the Einstein, modified Einstein method, which is the real one that needs to be studied, because that we may actually run. We may actually do the calculation. More so now that we have computer programs online. And I thought I was the only one that had done the modified Einstein online, but turns out that USBR has also done it. So I believe there's at this point at least two that I know. Online programs for the calculation of the modified Einstein. We believe that our program is a great program, of course, we always do. All our work is great. But I have not seen or have not tried to run. I'm not in the business of comparing outputs and so forth, but we're going to try it. We're going to try it, and I'm going to have you run it too, by the way. The modified Einstein, and we'll get there, is a step-by-step process, which was done by people at the USBR about 65, I believe, 1965 or 55, I'm not sure, but it was 50 years ago. And it's still there, and it's still timely, it's still being used, and it's still considered to be the ultimate way of calculating sediment transport, because it not only considers the Einstein method, but it's also done in a step-by-step fashion that allows the keep it simple principle, meaning it can be understood. It's a step-by-step, unlike Einstein, who tried to do a step-by-step and he didn't do it. And we'll see how he didn't do it. I guess it was too long a procedure to do step-by-step in the case of Einstein. So let's move on in here. Let's see what Einstein says. First, let's keep the historical perspective in mind. He wrote this paper, my guess would have been in 1948. He was working for the Soil Conservation Service of the time that later became the Natural Resources Conservation Service 50 years later. He employed himself as a soil conservationist with the Soil Conservation Service, and he had time and ability to write this paper. Maybe his bosses told him, if you're working on this, go ahead and write the paper. They gave permission to write the paper. And then right after that, he got found, I guess you could say identified by the people in academia, and he was offered a job at the University of Berkeley, and he took it. So from 1950 on, Einstein found himself teaching sedimentation at California, Berkeley. And he stayed there until he passed away. I believe he passed away in 1971 or 72 or 73, could have been around those times. So he was there for 22, 23 years in UC Berkeley. Okay. And he did a couple of things. He actually wrote a paper. He wrote a paper with a Chinese gentleman, Einstein, right. It's an interesting story, which I have not told, but I know because I read a lot. One day they had an interview. He gave an interview to somebody, and they asked him what he thought was his best contribution. They asked Professor Einstein, what's your best contribution? And perhaps anybody who was out there or that knew the subject would have immediately realized that he was going to say, oh, my bedload function. No, he didn't. He said that it was a paper that he had written in 1959 with a Chinese co-author, some gentleman, I don't recall the name right now. And it is in the reference, in the literature. If you're interested, you can go out there and look it up and see which paper of his did Einstein think that it was his best. So that must be a great paper. Myself, I have not read it, to be honest with you. You can't read everything. So there's too much information in there. But I'm telling you the story to show you that in many instances, when great people are asked what they think the best contribution is, their thinking or their idea does not coincide with that of the populace. The populace has a different story or a different view of things. Everybody thinks that this was the greatest paper that Einstein put together, and also one of the greatest papers in the explanation of sedimentation engineering that we're studying. That's why we're spending a lot of time on it. But he didn't think so. So he says, river basin development has become one of the largest classes of public enterprises in the US. That is correct at the time he wrote this. Right now, it is not. How did things change so, not quickly, because it's been, what, 70 years? They changed gradually, let's put it that way. River basin was popular in the 20s, 30s, 50s, 70s. By the 70s, 70s, 80, it had become something that we used to do, but now don't do it anymore. Your professor, Professor Ponce, studied when I was young. My intent was to get into dam engineering, not that the M-A-D-A-M-N, no, D-A-M-N-N, no, it's dam, D-A-M, dam engineering, reservoir engineering. That was my original intent. And I must confess to you, or rather, it's not confession, it's just a statement of facts, that over a 50-year career, I had a chance to work on 3 dams that I actually participated. And of course, do you realize that when a dam project gets put together, there's just not just one person, there's 10, 15, 20 people working on the dam, because there's specialties, this and that, and hydraulics and whatever, channels. So I worked on 3 dams in 50 years. If I had to work only with dams, I would have starved to death. 3 dams, 50 years, no good. But the fact of the matter is that being a hydraulic engineer and hydrologic engineer, for that matter, we had a lot of ground to cover, and we covered all sorts of things. And you can see my CV to find out exactly what we did in the last 30 years. But at this point, let's go back to Einstein. He says, almost every kind of river and watershed improvement program requires some degree of alteration of the existing regime. So he's basically talking the same kind of stuff that Lane was talking. But let's keep that perspective in here, the historical perspective. Lane wrote his paper in 1955, and this guy is writing a paper in 1950. So he's actually preceding in his observations what Lane said 5 years later. Yeah, right. The difference is that Lane got to be popular because he wrote a paper and he threw one equation at us. And that was the famous equation of Lane, which was a simple equation, by the way. This gentleman, Mr. Einstein or Dr. Einstein, is throwing hundreds of equations at us. So that, as you know, somebody said out there, somebody very notable and famous, said that the readability of a paper is in inverse proportion to the number of equations it has. So if a paper is full of equations, it's hardly unreadable. If it doesn't have any equation, it's very readable. A case in point, my Kerr number paper has very few equations. It's a very good paper. It tops the list of citations on my list. I have other papers that are full of equations. I have a paper on numerical analysis that's 90% equations. And that tops the list, the opposite, the bottom of the list of readability. It got so unreadable that not even the author, Professor Ponce, can read it 30 or 40 years later. I don't want to spend the time on that, rehash all that stuff. Forget it. So those papers are basically in the dump at this point because they're too complex. That is life. I didn't do it that way. It just happens that way. But I just wanted to share it with you. That's why Lane got to be so well read, because it's a relatively easy paper to read, relatively easy. And this paper is tough. Very few people have actually completely digested it all. And we're not going to do it either. Let me just go ahead. Okay. One of the most difficult problems encountered in open channel hydraulics is the determination of the rate of movement of bed material. Lo and behold, the movement of bed material is a complex function of flow duration, sediment supply, and channel characteristics. Flow duration? Do we know what that is? Well, you can look it up. Go to, if you are interested in learning what a flow duration is, you go to my book, my hydrology book, chapter 2, the last section. It says flow duration in there. Let's take a look if we can do that right now. If we can, I'm not sure, but we'll try. Engineering hydrology, chapter 2. Can you see what I see? You can still see it, right? Runoff, green page. I don't know. New share, I think it's new share right here. Right. Now you can see it, right?
Yep.
Yeah, now you can see it. You need to be refreshed, the share. So this is section This is section 2.4 of my hydrology book. And at the end of this section, we have the definition of flow duration over here. There it is. Flow duration. Flow duration is basically the duration of the flow in a channel. Practical way to evaluate day-to-day stream flow variability is the flow duration. So this is the flow duration curve that Einstein is placing a lot of attention. He just mentioned the flow duration. So we should understand exactly what the flow duration does. It is a curve that serves the purpose of comparing when you regulate a stream, as shown in there, regulated versus unregulated flow, and there's variabilities at the end of the 90%. So it's a kind of a somewhat of a statistical way of looking at the permanence, exactly, that's the word, permanence of a certain flow level, percent of the time. So percent of the time, 100% of the time, the flow is less than 7 cubic meters per second. 50% of the time, the flow is less than 20 meters, and so on and so forth. So that is the flow duration. Now let's go back in here. Okay, there we are. So granted, then the flow duration is, according to Einstein, something really important because he is going to, oh, I lost it, I guess. Didn't it? I lost it. No, I didn't lose it. It's right there. Are you seeing the Einstein paper or not?
We don't see anything at the moment.
Okay, fine. At this point, it got messed up. Yeah, happens when we manipulate this. Okay, I'm going to redo it. Okay. I had to bring it back. Okay, now we're okay, right? Right?
Yes.
It always takes you guys time to answer. Okay. So we're here back in page 3 of Einstein's paper, and he is going to be first looking. He has caveats before he gets started. He says, well, this is not what I'm going to do, and so on and so forth. He says, this publication does not attempt to give specific solutions for all sediment problems. Nobody asked him to do that. All we want to do is determine the bedload function, meaning the rate of sediment transport, only bed transport. Specifically, he says, I'm only going to be doing wash load. I'm not going to do wash load. Remember, just Professor Ponce just said that in our methodology, we don't include wash load because it's a can of worms, right? So in here, this tool is the bedload function. He calls it the bedload function, and that has become kind of a good phrase to use, the bedload function of Einstein. It has other ways of expressing it. Basically, most people call it the rate of sediment transport or sediment transport rate, which is the same as bedload function. Approach to the problem. The term bedload function has proved to be useful in the description of the sediment movement. It is defined as follows. The bedload function gives the rates at which flows of any magnitude in a given channel will transport the individual sediment sizes of which the channel bed is composed. And he's going to be talking about the movement of the bed by jumping and slipping as opposed to the suspended. But then eventually he's going to get also to the suspended. So interestingly, he says he's going to concentrate on the bedload function, but then once he gets the bedload function, he feels compelled to continue to find a suspended bed load as opposed to the bed load. Remember, we already talked about the classification of modes of transport very early in this course. So we must understand that already. So he moved from the bed load, from calculating the bed load to calculating the suspended load. And the calculation of the suspended load is going to be complicated by the fact that he's going to have to integrate two curves, the curve of the velocity profile and the curve of the concentration. Fortunately, the velocity profile had already been defined for a while now by lots of people that did early work or work prior to Einstein. And the concentration profile, the sediment concentration profile was studied extensively by Rouse, and we studied that already, Rouse and others, the Rouse number and so forth. So Einstein was able to use stuff in the late 1940s, late 1940s. They had already work that had already been done by several other people in the 30s and 40s prior to him. So now he goes into definition: bed load, suspended load, bed layer, bed material, wash load. Wash load is that part of the sediment load which consists of grain sizes finer than those of the bed. He's going to define that. Limitation of the bed load function. Functions often become constant or even equal to zero under a wide range of conditions. This is interesting because I think I already mentioned to you that we don't use the bed load function because it has a way of getting some indetermination. And once you get indetermination, then you can't do anything. You can't call Einstein to consult for you. He's dead already. So therefore, we try to avoid methodologies that don't work all the time. They're not foolproof. And that is why the modified Einstein is useful, because that is a foolproof methodology, thanks to Colby and Embry, that actually decided to fix the problems that the Einstein method had. So the Einstein method is very well respected and very well talked about, but it's not used in practice. In practice, it is not used. Not even Professor Ponce. At the beginning of my career, back in the middle 70s, I was using the Einstein function. And I eventually gave up because we got into some corner and we couldn't get out. And you're not going to spend a whole lot of time if you get into a corner where you can't get out of it. So then we moved on to the modified Einstein and so forth. I was lucky that my professor, Khalid Mahmoud at the time, said, Ponce, you're good with computer work. Why don't you do the modified Einstein? And I said, well, that's a challenge, but I'll do it. And we did it. It took us a couple of months to do this work, by the way, in the middle 70s. We were good. For Fortran, very good. As a matter of fact, I should tell you that eventually I wrote a Fortran book. Actually, I wrote a Fortran book, belatedly, but I wrote it. I say belated, but that's wrong, actually, because Fortran is still current. 50 years have gone by and Fortran is still current. But I wrote the book because I was good at it and I felt that it was going to be easy for me to do. That was in 1992. And I tried to get it published. And the publisher laughed at me. They said, Professor Ponce, Fortran is dead. What are you talking about? He said, really? I said, well, I'm sorry, but I think it's a good tool. No, nobody's going to touch it. We're not going to publish it. We can't sell that book. So then I decided to publish it on my own, which I did. And then eventually I put it on the web. Right now it's on the web. And I have had a couple of people, not too many, a few. For one person that thanks you, how can I say, sends you a letter thanking you, there's 100 people in the background that use the material, but didn't thank you. Let me tell you, I know what I'm talking, okay? And so I got a couple of good people that said, hey, Professor Ponce, we love your Fortran book. So I'm assuming that there's a whole bunch of users out there that are keeping quiet, but they're still using it. Why is Fortran being used? Even though it's 60 years old, 69, 1954, 54, earlier to 54, 50, 52, 54. 54, that puts it in the category of about more than 60, almost 70 years, say 60 years, because it remains the fastest, because it is the only one that runs on floating point, and it's all it does. It does floating point arithmetic. All the other methodologies that are around do everything. They stop at dancing. I say that jokingly. They do everything but dance. That's exactly the truth. Because everybody knows, and I should reiterate that to you, but you already know it, that 60 years ago, the only calculation that was done in a computer, in a CPU, they used to be called CPU, Central Processing Unit, was floating point arithmetic. 1.3 plus 3.7 equal whatever, 5, right? Millions of calculations, but floating point. Nowadays, it's done for everything, absolutely everything. Commercial, etc., Facebook, WhatsApp, and stuff like that. So the languages need to be more versatile. But at the time, they gained that versatility by losing their speed. Sure enough, that's the way. A case in point. I think I already mentioned that in my other class. We had a program in Fortran that would run in like 3 seconds, a complete computer calculation of groundwater. And we had a program in PHP because that was the method that we were using to put it on the web. And it ran in about 7 minutes. So from 3 seconds to 7 minutes. That is just one proof of many that we have that Fortran is the fastest, 10 to 100 times faster than anything that you see around. but it only does floating point. So it's basically contemporary practice, useless. Unless you put it together with another program that could do everything but, and have Fortran do only the floating point. Is Professor Ponce crazy or what? No. When you run HEC RAS or HMS, that's exactly what you're going to be doing. You're going to have all sorts of peripheral programs that are running the input output and the fancy stuff and the color and the pictures and the raster, so to speak. But by the time you get to the floating point, the developers, are going to resort to Fortran. Of course, they're not going to tell you. They're just going to run it and that's it. So beautifully, HEC-RAS runs in 1 second. It is amazing how many calculations HEC-RAS does in 1 second. And since you don't know, I mean, not you, but most people don't know that Fortran is running in the background, the sort of kernel that they like it, they say it that way. They don't know and they don't have any way of knowing because the Army Corps is not saying that. I don't think they're saying it in their manual, not in the user's manual. You know, there's a user's manual and a reference manual. So most people think that they're not using Fortran. I've been told by people that don't know. They say, oh, Professor Ponce, you still use Fortran. No, we haven't used Fortran in 30 years. You go like, oh, this guy doesn't know what he's talking, but that's okay. I'm not going to illustrate him. You know, people continue to use Fortran because it's hidden behind the large programs that we're using. So long story, and I'm going to finish in there. I got sidetracked in here, but let me just say that at this point, we are reading in here what, and I'm going to ask you to do this, to read this paper, which is important paper, but read it only up to here, up to the hydraulics. Once he gets to the hydraulics, he gets into the friction formula, and we could spend some time on it, but it's not necessary at this point. At any rate, if we really, really wanted to learn this, which would be unnecessary at this point, to be honest with you, because like I already told you, hardly anybody uses this method. So why am I going to waste your time? But the point is that from here on, he's getting into the resistance, he's getting into all sorts of mechanics in here, and even stochastic issues. And I'm not sure that you guys are able to get into stochastic. Stochastic is a whole entirely different ballgame than mechanics. And he's using both, as a matter of fact. So suspension and so on and so forth. And I just wanted to show you in here at the end, the integration and the graphs, the Einstein graphs that we endeavor to put in Fortran and in PHP, because let me just go 1 minute in here, then I'm going to stop. These are the graphs that Einstein put together with his own hand, presumably, or he had somebody drafted. I wouldn't be surprised if he did it himself. So these are the graphs that were put together in the back of the report. If you consult the report in the library, you'll look at the graphs, you'll see the graphs. So I went ahead and scanned the graphs to show them, right? Like I can show this graph over here, right? These are the functions of Einstein, okay? And I'm not sure I'm going to lose it here. Yeah, I did lose it. That's okay. I can go back. Okay, so these are the graphs. So in order to come up with the computer program, we had to digitize these graphs, and it wasn't easy, and it was a very much of a pain in the neck to digitize these. Digitize meaning discretize. So we had to express them in discrete fashion and then use piecewise linear interpolators, which we already had from the beginning. We use that all the time. So it's a tool that we cannot live without, the piecewise linear interpolator, to put into the computer just about any function that you care to invent or to develop. And that we did with the Einstein method, and we did it twice. We did it in the year 1975, 76 with the Fortran method, because we published this Fortran. And then in the year 2007, we had to convert it to PHP because we were going to use PHP. And we figured that it wasn't going to be too bad because there's really not a whole lot of computation here. You think it is, but it isn't. I mean, maybe 1,000, 2,000. What's that for a computer of the day? Nothing. It gets to be like in the case of the what am I going to say? The groundwater program, well, that's talking 20, 30, 40 million computations. That's why it took 7 minutes to run. So with that, I am going to now stop the share and say, basically, we have finished with this lecture. When I come back, I will start on Colby and Henry's modified Einstein next week, Tuesday. Thank you very much.